Okay. So suppose you have a metallic bar, probably made of steel or aluminum. You applying a uiaxial tensile stress. Once it's failed, you actually get a failing force, and you divide that cross-section area that gives you the failing stress. That is the ultimate strength. But for most of engineering material like metal, they have a yielding point before the final fail. So you need accounting both of them, the initial yielding part and the ultimate failure strength. So let's begin just to showing a video of how people are doing a tensile test.
Metal chucks that are locked into the machine.
Let me just make it louder. It's almost 100% here, but I can't. Okay.
Not held in place with metal chucks that are locked into the machine, and we'll see a close-up view of this in a moment. The horizontal beam, which is known as a crosshead, can be driven up or down and can apply forces of up to 5 tons. As this is a tensile test, the beam will be driven in an upwards direction, stretching the sample outwards. Each test machine has its own computer with various software packages to control different types of tests. You will be asked to measure your test samples before positioning them in the machine, and then enter the dimensions into the computer. As the test progresses, the computer plots a force extension graph on the screen, and you'll be able to print this out at the end of the test.
Okay, tests are beginning.
Okay, so the test has just started, and we can see that the sample is being stretched outwards. That little kink that you've just seen in the graph is known as the yield point. That indicates the transition between the straight line portion and the curved part of the graph, and indicates the transition between elastic deformation and plastic deformation. We're about to reach the peak of the graph. The peak is known as the U point and indicates the ultimate tensile strength of the material. Beyond the U point, the material is weakened and the force is falling off. Beyond the U point, the material is on its way to failure and nothing can stop it from failing now. Can you see how the sample is beginning to reduce in diameter? This is known as necking, and the sample is about to fail. We've just seen a sudden dramatic failure and we're left with a jagged fracture.
Okay, that's stop. So actually you can see this very typical load displacement curve. And after the test, the metal bar kind of gets some necking effect in the middle, and finally it failed. So now I want to show you a typical curve and how to interpret that. So let's draw if you divide the force across the original cross-section area, then you get the stress. So today is week 3. Oh, yes. Thanks. Lecture 6, okay. Plasticity. Okay, let's just draw this stress-strain curve. So what it looks like, let's draw the axis first. So in the x is the strain, and the y-axis is the stress. So initially you have a linear elastic region. And then followed by the yielding point, which the material start to diverge from the linear elastic line until you reach a maximum point, and then the material start to neck, and the cross-section becomes smaller and smaller, and finally it felt in some point here. So let's interpret this curve. So any questions in the back? Okay. If not, please just keep silent. So let's first look at this yielding point. This is probably not the right interpretation. Most of the time, we are doing that is we draw an offset line which is parallel to the initial linear elastic line. And there's an intersection here. How much for that offset? Most of the engineering books are suggesting 0.2% of strain. So that actually gives you the point where yielding happen, and that gives you the actual yield strength you normally use for determining how strong your material it is. And there's another point which, when you reach the maximum, we call it RUTS, which means ultimate tensile strength. And from this point, material start to have some necking effect. Okay? So why there's such strange curve? Yeah, there's some micromechanics, like dislocation behavior happens around here for most of the metal. That's in the microstructure. And when it homogenized together, it's showing a behavior like that. So one typical behavior for a plastic deformation is when you unload it. For example, you unload the curve here. Let's use another color. It will follow the same gradient, but it will never come back to the origin point because you are actually generate some permanent, let's call it plastic strain in this part. And this part is still recoverable. We call it elastic strain. And this is the total strain, epsilon t. Okay? So normally we can write epsilon t equal to epsilon p plus epsilon e. Elastic strain and plastic strain. And what happens when you loading the material and there's a highly localized region, which I think I already showing you in this video, this necking effect. The reason I'm showing you this is because some definition of strain and the stress is affected by this necking effect. So let's say this is a highly localized deformation. Okay. So there's some terminology I wanted to define. First of all is the strain we are plotting here is, let's call it nominal strain. Or you can call it engineering strain. Okay. So what the definition of that is what I have shown you before, is basically epsilon equal to the delta L, the changing of your length over your original length. So this is refers to undeformed configuration. But there is another measure which you probably heard that before, called true strain. What true strain means is because you actually have a necking effect, so in that part, the localized strain is much higher than the rest of the material. And if it is really a large strain, like 50%, your engineering strain is no longer representing the behavior of the material. And for true strain, probably it's more accurate, I would say, for large strain problem. By large strain, I would say maybe larger than 30%, let's say. There's a lot of definition, but I think 30% is very large already. So what the definition of the true strain, how you can get that? So now we define that is true strain using another parameter called phi. Let's first look at just a small amount of displacement. I mean, the sample haven't yield. You just look at a small amount of strain. You can still write like a similar equation like the nominal strain. But now, when you divide a value here, L, which you need refer that to deformed state. So every time when you load the material, there's the material elongate and become longer and longer, and the length here is become larger when loading the strain. So that's actually changed every time. So that becomes very hard to get that value, but we can still derive that. So we basically, suppose you're loading the material from original length L0 to L1. We actually integrate this tiny little strain from the beginning L0 to L1 of this tiny little strain. And we do some math just to work out the result. So basically, if you remember, this 1 over L, do the integral is ln L, and from L0, L1. So that is ln L1 minus ln L0. And this is equal to L1, L0. And if you rewrite this, the top one, L0 plus delta L over L0, that gives you this 1. You cancel that to become 1, and this is equal to epsilon. So epsilon is actually the engineering strain we already defined from here. So that's the relation between that to that. So this can be even simplified if you do some math, which is using Taylor series. So that can be even simplified to what do I mean by Taylor series is, I'm not sure that is very useful, but just showing you the result, I think that's more useful to see the physical meaning. That's the Taylor series. You basically you expand these expressions with a lot of high order term. Here you times the square of epsilon, and that if you cancel the high order term, what you get is a much simpler equation, phi equal to epsilon minus half of epsilon square. So that is the final equation for true strain. Okay, so for most of the time for small strain, the true strain is almost equivalent to the large strain, this true strain. They are the same. You don't make any difference between them. But for large strain, they actually have a big difference, because now you can avoid this term, this square term. It's not negligible. So let me show you the actual curve if you plot these two together. So if I plot the engineering strain and the true strain, so engineering strain is the dashed line here. It's basically a linear line. But if you plot this true strain, you will see actually it starts to diverge if the strain increased. In that direction is the tensile strain. In that direction is the compressive strain. So you couldn't avoid that happens. So you need to consider the large strain problem. If you doing this calculation, you need to use the true strain rather than the engineering strain. Just to give it an idea, the definition. Most of the time, we are still in this small strain problem. Okay, that's the definition. But similarly, you probably also heard there's some called, yeah. Engineering stress or nominal stress. Basically, is the one we already draw in that stress-strain curve. So you have your force over your original cross-section area. That's the undeformed state. Cross-section area. Okay? But for the true stress, you need to consider in this necking effect. Let's say true stress, true, T. Now the force is the same, but the cross-section is keep changing. So you need considering this deformed cross-section. Especially, you need actually consider that necking part. So the question comes now, which one I should use in most of engineering applications? The answer is basically why it's called engineering stress and strain is we use it in our engineering problem. So we don't use in true stress and true strain in most of the case. Partially because for the true stress problem, you see this cross-section areas keep changing. You couldn't measure it accurately. And also for design problem, you're not expecting that bar is deforming. When you design, you assume that is a constant cross-section at the beginning. So that makes everything easier to follow. Otherwise, everything is changing. You couldn't do accurate calculation. So just to give you this definition, in the future, maybe people ask you what is true stress, and you know how to answer that. Okay? And let me now, it's really interesting. Now we go into this plasticity theory. That's, I would say, one of the key part in this course. Let's put a star here just to emphasize that. So what is plasticity theory? So basically consider there's a two part of that. One part is the yield criteria. This basically to predict the initiation of yielding. So RP, this is the yield strength. And second part, flow rule. That's governed after the yielding points, how the plastic deformation happens. So you need to give a rule how this plastic deformation goes. This is after yielding. And most of our focus is on the yield criteria. Okay? This part is not that important in this module. There's hundreds of different theory for yielding criteria and flow rule. But I will only give you two classic one. Can you remember that if you had your course before? Two classic yield criteria. Von Mises, yeah? Tresca, yeah. Excellent. So let's go through that. So before we really define any yielding criteria, we make our assumption here. Just make our life easier. Assumptions. First of all, the material is isotropic, such as metal. And the material is if it is yield, the yielding happens mainly due to the shear dominant stress, which is relevant to this deviatoric stress. Okay? That's the two assumptions. And let's start from some general stress state. Okay, so because most of our material we measure is apply a uiaxial loading and we break it, so we get this value, yield strength, we call it RP. But for most of the general problem, for example, any engineering structure like a bridge, they all undergo different loading case. It's mostly multi-axial 3D loading case. So it's not uniaxial loading. So our aim here is to make it simple to calculate the result, to predict the yielding, rather than using this very complex 3D general stress state. So let's define the general stress tensor. If you remember, we just write that sigma y, sigma z. Okay, so that's a general stress state. It's really not practical to use that to predict a failure because stress is acting everywhere. That's why I spent like 1 week to prepare you to using another theory, which is the principal stress state. So that kind of reduce your parameter to just 3. Oh, sorry. Our notation here, let's just make life easier using the small 1, 2, 3 rather than use the room number. Okay, 1, 2, 3. That's principal stress. Now we only need to consider the principal stress because there's no shear component here. They're all 0. Okay? And how are we going to do that? Let's recap here another thing. Hydrostatic stress. Most of you probably don't understand the physical meaning. Let me just make it more clear to you. Okay, let's just first talk about this hydrostatic stress. So suppose you have a cube. Okay, you put that in the water like that. So basically, the water will give a hydrostatic pressure from everywhere. And the stress is basically only acting on the surface as a normal stress from 3 directions. So hydrostatic stress basically is the condition of equal stress in the all 3 directions. So without any shear stress. So by that means, now you are plotting the stress in the principal stress space. Sigma 1, 2, 3. And there's no shear stress here. And hydrostatic stress is when these three stress is equal. So when I tell you hydrostatic stress is when you calculate that is the mean stress of sigma 1, 1. Yeah. Let's just do 1. Yeah. Sigma 1, 1, sigma 2, 2 plus sigma 3, 3. This notation means that is in a general 3D notation, 3D tensor, okay? But if it is also equal to the principal stress, so what happens when sigma 1 equal to sigma 2 equal to sigma 3? So hydrostatic stress is basically equal to them, right? So if you look at the slides here, basically this hydrostatic stress is, if you have a vector, which is this red vector, in this vector, all the stress components is equal. And this is a unique stress axis which acting a point where there's no yield stress happen. Because in the experiment, when we load the material in this hydrostatic stress, like put that in the water or like oil, you actually doesn't introduce any plastic deformation on the material. The material just shrink or expand in volume, but doesn't change the shape. So that is the physical meaning of hydrostatic stress. Since we are considering how to predict the yielding, this part doesn't contribute to any of the yielding part. So we need to subtract the hydrostatic part in our calculation. So that will be relevant to our Von Mises criteria. Okay. That's one recap. And the other two recap, I think probably is useful to let you know what is the plane stress state. Suppose I have just a paper here, very thin sample. So in the through thickness direction is almost minimum, is nothing. So if you're loading that, suppose you have a Poisson ratio or anything happens which will cause some contraction in the through thickness direction. But because the thickness is so small, you actually generate nothing on the stress. So that is called plane stress, which means stress component in the through thickness direction, sigma 3, or sigma z here, is equal to 0. You just need to remember there's nothing, for example, these three components, anything relevant to the z, the through thickness direction, will equal to 0. Okay? So when you write your stress component, that part is 0. You can simplify to a 2D problem. But most of the case, in our hydrostatic calculation, you can't avoid that because still it is a 3D problem. So I will give you an example on a problem on like plane stress problem. So similarly, there's another scenario where you make your through thickness extremely large. Make your thickness extremely large. What happens? Something like that. You make your thin paper to a block, I would say, very thick block. So the thickness is so large, so any stress in this in-plane direction wouldn't make any effect on the strain. So that means in the through thickness strain is 0. So mathematically, you should look at the bottom part. So sigma epsilon zz is equal to 0, and anything like shear part which has a z component here should equal to 0. So give you an example like a roller in a bearing. So in that horizontal line, that's the thickness direction. If you apply any load from the side, you actually doesn't generate too much strain on this roller, right? And also another example is a dam. So you apply the stress from your water. Let's say this is the in-plane, the horizontal direction. But the through thickness is this one coming towards us. The dam is extremely long in the thickness part. So that doesn't generate any strain in the through thickness direction. Okay. In case someone asks you plane stress and plane strain, what that means, just remember that equation. 1 is the bottom for that one. Epsilon zz equal to 0 for plane strain. And sigma zz equal to 0 for plane stress. Okay. So let's go back to our failure criteria. Tresca. Yeah, I keep forgetting, sorry. So Tresca yield criteria. It's interesting in the mechanics world, a lot of theory is associated with some big guys. So like this one, Tresca, is the name of a scientist. But that doesn't tell you anything. It's just telling you need to remember this guy. But the more interesting or have more physical meaning is maximum shear stress criteria. That's how you interpret that criteria, okay? Why is that? If you look at these slides, I'm actually loading it in a uiaxial condition. So that's from this red arrow. But the material actually failed in a 45-degree angle for isotropic metallic material. So that actually means this criteria is relevant because your maximum shear stress, if you remember how to get that maximum shear stress, because principal stress is in that direction. If you look at that component, there are 3 stress components. Only there is one is positive, and that must be the maximum principal stress, sigma 1. And all the others are 0. And the direction definitely is along that direction as well. Because maximum shear stress direction is at a 45-degree angle with regard to this principal stress direction. So that is the maximum shear stress direction. And that causing the failure of the material. So it's very simple criteria, actually. If you give me the maximum shear stress, I know how it failed. But most of the case, you only get one value from this uiaxial tension, which give you this uiaxial tensile yield strength, RP. So my question is how to relate RP to the Tresca yield criteria. Okay, how to relate that? Because in the end, we want to use this value rather than using the maximum shear stress, although they are kind of, they can relate it by some equation. Okay, so let's go to the Tresca yield criteria. So now the question is here, how to relate to that, because maximum shear stress is tau max. So basically the question is how to relate RP to the tau max, right? The only thing we know from our calculation is we convert the general stress to a principal stress. So we will get sigma 1, sigma 2, and sigma 3. And we will assign that sigma 1 at the largest, sigma 3 at the smallest. So what the equation for the maximum shear stress? The way I remember that is I always draw more circle. Let's say more circle. This is the normal stress. This is the shear stress. For a 3D problem, now is a 3D problem. Let's say this is the sigma 3 and sigma 2 here, sigma 1 here. So more circle, I normally do like this. If I know this principal stress, I just need 2 points. One and this one will give me this circle. And since it's a 3D problem, actually, you need to draw another 2 circles inside this. Just remind you, but this is not relevant to determine the maximum shear stress. So maximum shear stress is here. If you look at this shear stress line, maximum and the minimum, so this is the tau min, this is the tau max. Since it's a circle, if you have a line here, you rotate it, so their length is the same. That's why you can relate this length, let's say here. This length, which is equal to, let's say L, is the length equal to this minus that, right? Sigma 1 minus sigma 3. That's basically the diameter of the circle. The diameter of the circle. And if you ask me what the tau max, it's basically half of the length. So tau max is half of the length, is equal to, right? That's how I remember it. I don't need to remember too much equation. Just that is enough to let me interpret this tau max. Okay? So the yielding criteria for Tresca basically is once the tau max reaching the critical shear stress, it will start to yield. And if I substitute my equation here, so that give me 2 sigma 1 minus sigma 3 should be smaller than that, otherwise the yield will happen. Okay, that's the yield criteria. And now, let's just look at the simple uiaxial tensile test case. So for this case, what happens is sigma 1 principal stress, let's say it will fail at RP. Failure here. So sigma 1 will equal to RP, right? Sigma 2 equal to 0. Sigma 3 equal to 0. Bear in mind, this is the principal stress. So you could write that in a capital. Okay? So when you substitute this condition to that equation, okay, what's happened is you have RP minus 0 smaller than the shear stress. Now, from that equation, actually, I know how to relate my maximum shear stress, critical shear stress, to the uniaxial tension test.
So, why is sigma 3 0?
Sigma 3 should be 0 because it's a uniaxial test. There's no loading in sigma 3 direction. Okay? So that basically gives you the relation between your critical shear stress with your measured yield strength. So now, the really Tresca criteria here. is I put that equation back to here. So let me just put equal here, because this is to get this relation. Tresca criteria by substitute tau c into equation 1 here. So you actually get this. You relate the principal stress with your measured yield strength. So that can be simplified to RP, right? So from that logic, you can see actually I relate the principal stress with the measured yield strength, because this is the only value I know from my test. And this is the easiest way to get yield strength of a material rather than do a shear test. Okay? RP is the one I draw here. So RP is the yield strength, if you look at here. It's a 0.2% offset of your initial line. And there's an intersection between your stress strain curve with this dashed line. So that gives you the yield strength. Okay?
Thank you.
No problem. Okay. So that gives you the criteria, which looks very simple. I would say very easy to understand as well. More interestingly is, okay, let's have a break. Okay, let's come back to the lecture. So if you look back to the equation here, it's very simple. Basically, if you are given a 3D general stress state, so what you need to do, step 1, you convert this multi-axial stress state into a principal stress state. So step 1, just change that x to principal stress state. Let's say P. And then you know you have these 3 values. Then work out sigma 1 minus sigma 3. So if this value is smaller than your yield strength, the material is safe. Otherwise, it starts yield. Okay? So looks very simple. Okay. Let's visualize this criteria. Suppose we are in a plane stress state, which means sigma 3 equal to, let's say, sigma z. That's the general state. Sigma z equal to 0. But accordingly, sigma 3 in principal stress is also equal to 0. Let's plot. We plot sigma 1, sigma 2 relation, which is in a principal stress space. Okay, so by that I mean now you have 2 axes. One horizontal, you put that sigma 1. The other one is a vertical one, sigma 2. Because sigma 3 is 0, we don't need to consider it in this scenario. how I draw the Tresca yield surface. Let's draw this yield surface for Tresca. Okay? So what I normally do is, I know the yield strengths I measured from the experiment RP. For uiaxial test, tensile test here, and another one, compressive test, negative RP. And if you do that in transverse direction, similarly, the yield strength is the same. RP here, negative RP here. It should be equal, but here looks like not equal, sorry. But basically, I do it, I just connect this line and connect this line. I will explain that to you later. So how you draw it is simple. It's just you draw this line. So let's say this is number 1. This is number 2. So what number 1 means? So in this line, since we have sigma 1 larger than 0, sigma 2 larger than 0, sigma 3 equal to 0. Now we know actually the principal stress, we will assign that sigma capital 1 equal to sigma 1. Yeah. And sigma capital 2 equal to, now the smallest one is 0, which is in this one, plane strain, plane stress state. So now you know these two values. So remember the Tresca criteria is sigma 1 minus sigma 2 smaller than the RB. Okay, let's just let that equal so we can find the yield surface. The yield surface means they're just reaching that yielding point, means just equal to RP. Okay? So let's put that into that equation. You get sigma 1 now is equal to RP, right? So put that equation here. This is 0 and this is sigma 1, and that means sigma is RP. This basically gives you the line, number 1, that vertical line. So it doesn't matter where your sigma 2 is. This line means whenever your stress along the sigma 1 direction reach the RP, then you start to yield. Similarly, for number 2, this one, sigma 1 larger than 0, sigma 2 larger than 0, because they are in this phase, everything is positive, and the sigma 3 is still 0. Now you need to be careful. Sigma, the largest one now is the sigma 2 in this line, okay? Sigma 3 is still 0. Okay? Because sigma 1 can vary from 0 to RP, but sigma 2 in this line is always RP. So it always means sigma 1 smaller than sigma 2. That's why you assign sigma capital 1 equal to sigma small 2. Okay? So put that equation to here. Again, you will see actually that is equal to sigma 2, equivalent to RP. Okay, that's give you the number 2 line. That's the horizontal line here. Mathematically, it's just that equation. And number 3 and number 4 is, let's say number 3 is just you connect these 2 points. Similarly, you connect these 2 points. It's kind of a hexagonal shape of this Tresca yield criteria. So let's look at number 3. Number 3, you have sigma 1. Now, sigma 1 in that part, left part, that part is negative. Sigma 2 in number 3 region is positive if you look at that area. Okay? Sigma 3 still is 0. So this is to work out the principal stress. Principal stress 1 equal to sigma 2 because that is larger than sigma 1. It's positive. Sigma 3 now is not 0 because you need to consider the negative one, which is sigma 1 here. So which now give you, put that to, sub that to equation 2 here. You have sigma 2 minus sigma 1 now equal to RP. Okay? That gives you this line, line 3. Similarly, for that line, I would say sigma 1 is larger, sigma 2 is negative. So now you assign sigma 1 equal to sigma small 1. Sigma big 3 is equal to sigma 2 because this one is negative. Similarly, sub that to equation 2. Now you get sigma 1 minus sigma 2 equal to RP. Okay. So looks like that. There is incline, this line.
Sorry, sir. Why is sigma 3 not 0 anymore for 3 and 4?
So because you need considering the smallest one as the sigma capital 3. Now this sigma 1 is negative, you see.
Oh, yeah.
So actually,
Yeah.
that's the smallest one. And so what these two mean actually is if you remember your math course, how to draw an inclined line here. So this is basically, let's say, if sigma 2 is the variable y, sigma 1 is the variable x. So this line basically is x minus y equal to RP. So you arrange it, looks like y equal to x minus RP. Probably you are more familiar with equation like that rather than look at the stress, okay? But essentially the same. This is the line equation for a line. Any mathematic equation for a line is like that. So it has a positive gradient, which is this one, and the intersection is this value. Okay, you can check x equal to 0, which is this one. X equal to RP, which give you y equal to 0, which is this one. Right? So that's some physical meaning of that. So inside the yield surface, this is the, let's put the green mark here. This is safe. all this area inside is safe, but outside you have failure. Okay? So that's very informative, because if you have this yield surface and you give me any combination of sigma 1 and sigma 2, I just put a dot here, that information into this curve, into this circle or into this surface, you will find it is yield or not yield, right? So that's a very informative graph. So let's move to another part, which is more kind of a classic, I would think, Von Mises criteria. Okay. Let's write from another new paper. Von Mises Criterion. Again, this actually makes no sense to me at the beginning. What that means, Von Mises, this person makes some contribution to the world, and we remember that. Okay, let's write the more physical part. It's called distortion energy failure criterion. Okay, I introduce a new theory to you, a new concept. Let's just write the definition. So let me read it and write it. Definition. So that means yielding will occur when distortion strain energy density. This is something you are familiar. Strain energy density reaches or exceeds the distortion energy, strain energy density. It's a very long sentence, sorry, but when you read it, you probably make more sense. For yielding in simple tension or compression of the same material. You say, well, what's that means? Basically, it's, you have a criteria here, strain energy, called distortion strain energy density. Once it reaches a critical value, for you're doing a uiaxial test, that will also give you a strain energy density. So these two equal, then you have a value, which means that yield. So again, we are trying to relate a thing to the measured yield strengths, which we know. Okay. Still not making sense, I know. So let's first of all introduce what is distortion energy density, strain energy density. So we have the total strain energy, right? Energy density, which we know how to calculate. Basically, this distortion strain energy is, you use that to subtract the hydrostatic strain energy density. Now it's making more sense because we are saying the hydrostatic part doesn't make any contribution to the plastic deformation. So we need to subtract that in an energy form. So that gives you the distortion strain energy density. Let's just simplify this word, strain energy density. Okay, so how we go through that? It will be a long math, but after you go through that, you really understand the physical meaning of Von Mises criteria, rather than I give you the equation and you don't know where it comes from. Okay, so to get this hydrostatic strain energy density, we need first of all to let you know total strain is also equal to hydrostatic strain plus distortion strain. So there is volume change here, but no shape change. Distortional strain, shape change, and no volume change. Okay? This is more like the deviatoric strain, distortion strain. So I think it's the same meaning. Okay, so let's first write down the strain energy density in the principle. So we will make everything easier to calculate. So you will do that in the principal stress space without any shear stress component. Okay? So if you remember, I will just give you the answer. The strain energy density in the principal stress space is basically epsilon sigma 1 times epsilon 1, sigma 2 epsilon 2, and sigma 3 epsilon 3. You can read your last lecture notes. You will get that. Okay? It's basically you integrate the area in this triangle. That's equal to half of that. But because it's integrate over the whole volume, so you have to sum them in three directions. Since epsilon 1, which is this is the strain, and if you write that in terms of the stress, you can write that like that. If you remember again, I have shown you that in the previous lecture. Similarly, epsilon 2 is equal to that. Okay, similarly, etc. for epsilon 3. Now, total strain energy density, UP, you subtract all this into that, okay, into that equation. So UP will give you the result. Minus 2 mu, sigma 1, sigma 2, plus sigma 2, sigma 3, plus sigma 3, sigma 1. Okay? So what I want to do is work out the hydrostatic strain energy. And using this total energy minus the hydrostatic strain energy, then I have this distortional strain energy density. So if you remember hydrostatic stress, that give you sigma hydrostatic is basically the average of all these principal stress. And now what that means is in the hydrostatic condition, sigma 1 equal to sigma 2, sigma 3 equal to this hydrostatic stress. So basically, all these components are the same. They are the same value as the hydrostatic. So substitute into this equation. What you get is the UP equal to 2. So you can see here there's a 3 sigma hydrostatic, and this is again 3 sigma. Here you have this one. Here you have this one. You can take them out. Minus 2 mu. Okay? Now this is kind of for an equation. I simplify that. And now you can put this hydrostatic part square. Okay? Put that back to this equation. It's a long equation, I know. So after many dots, so basically you just need to understand the physical meaning. If you don't want to copy that, doesn't matter. I will scan that to you. And you will see why it comes through to the Von Mises criteria. After many dots, after doing that, what happens, this hydrostatic strain energy density is equal to 612 mu, and then these parts plus together okay. That's the kind of final part for this hydrostatic strain energy density. So you know distortional strain energy density equal to the total strain energy density minus hydrostatic strain energy density. So now it's become more clear, like what's going on next. So finally, so you know this total strain energy is already here. Let's say this is the equation 3 and equation 4. So once you have this equation 3 minus equation 4, the final distortion strain energy density is simplified to this one. I hope you can do that yourself and you can verify whether your calculation is right. It's not that difficult, just linear algebra. So now you will see a much cleaner equation when we subtract that hydrostatic part. Okay? Looks much familiar to you, right? if you just look at that part. And what I wanted to say is, now we want to link these kind of things, distortion energy density, link that to my measured. So what do I mean measured? Measured strain energy density, measured SED, in uiaxial at uiaxial loading. Okay? So you have a kind of arbitrary stress state, but you have another state you measured from your experiment. So the condition for that uiaxial test, again, sigma 1 is equal to the RP, the yield strength, and sigma 2, 0, sigma 3 equal to 0. So what you need to do is put this to this equation 5. To equation 5. Then you get this simplified version. So now you get distortion strain energy density at yield for a tensile specimen. Okay, which give you, if you do that, sigma 2 going here 0, sigma 3 0. So it's much simplified. You only end up have this sigma 1 term, which have 2 in the end is 1 plus mu times to sigma 1 squared. And sigma 1, you can put that in, is equal to Ry squared. Okay? This is the thing you measured. So now we can finally compare the strain energy density of this tensile sample with a general case. Right? Now you actually have equation 6. Now compare 5 versus 6. What that give you? You will see the final simplified version after doing this. Equal to Ry0. Okay? So if you want your material in a safe region, basically you put a mark here, smaller than that, and you cancel this part. So finally you actually get this Von Mises criteria. Okay, I think most of the course, I also attend my solid mechanicals, and nobody tell me why this comes from that. So that's why I think this really gives you the physical meaning. Why this complex equation comes from this simple idea, distortional energy density. So you will see that is the criteria. So you do the square root on both sides, okay? Then you get familiar with this equation. And that also links you to the knowledge of this hydrostatic pressure or these things. Otherwise, why I need to tell you this hydrostatic part for so many times? Okay. Now you see, actually that's the Von Mises criterion. But if you look at how to write this or remember this, it's not that difficult. It's all symmetric. If you have a sigma 1, 2, there must be another 1, 2, 3. They are not repeated. Sigma 3 minus sigma 1. So each of the stress term appear twice. And doesn't matter the way you write it because they are a square term. So doesn't matter you write the other way. The answer is the same. Okay? So this actual term, let's call it Von Mises stress. This part is the Von Mises stress. So how many of you have using the Abacus or finite element software? Yeah? A lot of you? Yeah, good. So when you look at the result, they're always showing you this Von Mises stress. That's the reason why, because that gives you the scalar, only a one value, which you can compare with your measured yield strength. So that's pretty much the answer. Like, you give me the Von Mises stress. If it is smaller than the yield strength, then the material is safe. Otherwise, it yields. So that gives you the physical meaning of that. And it basically relates the principal stress, again, to your measured yield strength. Quite simple, right? So step 1, change that to principal stress. And now put that principal stress to get you a scalar value of Von Mises stress and compare that with your yield strength. So that's how you approach this kind of things. Okay? So let's look at a special case when it is a plane stress state. Which means sigma 3 equal to 0. So that term can be even simplified to, if you substitute this term into that equation, so you cancel that many term, and you just get this answer for plane stress. Okay? Sometimes we will use that. Most of the case in your probably exam, you will end up just need to know that plane stress. For a 3D more general problem, let the Abacus or some software to do that. You don't need to do that. Okay? So similarly, once you have this criteria, you can visualize that by draw a yield surface. Yield surface for Von Mises. Okay? Okay, how to draw that? Okay, basically what I'm doing is very similar to the Tresca yield surface. You first of all draw this axis, two axes, and the easiest things I normally do is I draw both of them, Tresca and Von Mises. The more you draw, the more you're familiar with that, okay? So the Tresca, basically you connect this as a square. Connect that as a square again. And connect this line and connect that line. Okay? Once you finish that, then the Von Mises criteria is simple. You have 6 identical points, which is equally represented by the Von Mises criteria. Now you just draw ellipse just by hand. I don't need some special tool. Okay? Okay? You're better than me, so don't worry. Okay. Like a watermelon. Okay. So it's actually simple. You just do that exercise and then you get this Von Mises criteria. That's enough, just by hand. I don't need to use very complex tool. So you noted that Tresca criterion. And this is the Von Mises. Okay? So there's some interesting point. Let me point that out. So there's 3 statements. Tell me it is true or false. It's true or false. Okay. Statement 1. If Tresca criteria, for Tresca criteria, there's no yield for Tresca criterion. And the conclusion is there is also no yield for Von Mises. True or false? True, yeah. So if you look at that, any area inside this box, safe. So look at the boundary. Basically, Von Mises is a more smooth version of Tresca, and they have some extra area to allow the material in a safe region. So Tresca is more kind of critical, but Von Mises allow you to have more area in that part. Okay, safe and failure. Another statement, if Von Mises yield, Tresca also yield. True or false? True. Because if you look any point outside here, if it is outside the yield surface, it means the material failed. So that means Von Mises yield, Tresca must yield, because Tresca is smaller than the Von Mises. Okay? Another one is if Tresca yield, it doesn't mean Von Mises yield. True or false? True. Because if you look at some points, like the dash point here, here. So it outside the Tresca yield surface, means it yield for Tresca, but for Von Mises, it's still within the yield surface, so it doesn't yield for Von Mises. So that raised some questions. Which one I should use in most of our engineering applications? Yeah, actually there are not too many differences, so both are okay, I would say. But if you really push the boundary, then Tresca. But for most of the computational calculation, if you're using abacus, they will much prefer this smooth version because that will reduce some convergency problem in your calculation. There's not sharp corner in the Von Mises. So computationally, you will prefer Von Mises. And mathematically, I would say also Von Mises is much beautiful. But Tresca is just simple version. And both okay. Doesn't matter. So someone really doing the project and saying which one I should use in the abacus. So I would suggest using Von Mises if you want to calculate something. That gives you probably more easy